Forget the night sky, Erase the glowing galaxies and the glittering constellations. Picture instead an absolute suffocating void, a space so completely devoid of light that it borders on sensory deprivation. It is tempting to think of the Big Bang as a blinding flash that permanently lit up the cosmos. But in the immediate aftermath of that violent expansion, despite the unimaginably dense heat and raw energy surging through space, the universe remained entirely dark. Welcome back to Actual Space. In our recent documentary, How Does Light Actually Work?, we explored the physics of how photons travel to our eyes. To truly understand light, we have to go back to a time when it couldn't travel at all. If the cosmos spent its earliest epoch as a perfectly lightless expanse, we have to ask a mechanical question. What specific physical trigger finally flipped the switch and turned the lights on? The timeline begins roughly 380,000 years after the initial expansion. The sheer heat of the early cosmos had finally begun to cool off, dropping significantly across the expanding volume of space. Cooling temperatures allowed protons and electrons to bond into a thick fog of neutral hydrogen gas. This physical barrier meant a stray photon couldn't travel. It would slam into a hydrogen atom, instantly absorbed and scattered. This dense atomic trap locked the cosmos into the cosmic dark ages. Even if a brilliant light source existed within it, its glow would have been entirely invisible to anything beyond its immediate reach. Out in that suffocating dark, gravity was the only active force. It worked silently, slowly drawing immense pockets of this neutral hydrogen gas toward each other. Over millions of years, these gas clouds condensed into staggeringly heavy clumps. As the hydrogen molecules packed tightly together, the internal friction surged, driving the pressure inside these pockets to extremes. Eventually, the heat at the core of these massive clouds crossed a critical threshold. It triggered nuclear fusion. The crushing pressure forced hydrogen atoms to fuse into helium, igniting the very first sources of light in the dark. Astronomers identify these original bodies as population 3 stars. If you look at massive modern giants like Betelgeuse or UY Scuti, they are entirely dwarfed by these early bodies. The original stars were wildly massive and burned fiercely hot compared to anything we observe today. Because of their immense size, they burned through their fuel quickly. These short-lived, unstable monsters provided the exact brute force engines the universe required to start fighting back against the darkness. Igniting the fuel was only half the problem. These population 3 stars were burning with intense brilliance, but they remained deeply buried and smothered inside trillions of miles of opaque hydrogen fog. Their extreme temperature provided the solution. Burning at such high heat meant these stars emitted lethal, massive torrents of extreme ultraviolet radiation. This extreme UV radiation operated like a blowtorch, violently ripping electrons away from neutral hydrogen atoms. This dismantled the physical barrier, allowing each star to carve out an expanding bubble of clear space that eventually merged, clearing the void. This violent physical phase transition is known as the epoch of reionization. It was the definitive mechanical event that permanently shattered the primordial fog, shifting the universe into a transparent state. With the thick gas completely incinerated, the physical roadblocks vanished. A photon of light could now leave the surface of a star and travel freely in a straight line for billions of light years. To verify this history, astronomers needed a way to look deeply enough into the past to observe those specific early stars. That required the James Webb Space Telescope, humanity's ultimate deep space-time machine. Getting this specific observatory off the ground took many decades of engineering. It was designed from the ground up to hunt for the faint traces of the universe's first light. This illustration shows what James Webb is calibrated to detect. As the extreme ultraviolet light from those early stars travels through space for billions of years, the expansion of the universe physically stretches out its wavelength, shifting it into the infrared spectrum. By capturing this severely stretched infrared light, the telescope allows us to literally look back across time and photograph the exact era when the universe first turned on its lights. Every glittering star and complex galaxy you observe in the night sky today shines clearly because of that dark age. They exist safely within the clear vacuum forged by those early monsters. To secure your spot on our ongoing journey through the cosmos, make sure you're subscribed. Head over to our Community tab and let us know on our latest poll if you've subscribed to Actual Space. You can vote yes or doing it right now. While you're there, drop into the comments and tell us what topic we should tackle next. Are you most interested in the latest JWST discoveries, the mechanics of black holes, or the newest alien news? The vast, illuminated cosmos is a lasting, transparent monument built by the brief and violent lives of the very first stars.